We are still on flat space-time, and we understand that this Cauchy problem has a unique solution. Which is the Pauli-Jordan function. You can use the Pauli-Jordan function to solve a generic Cauchy problem like this with initial data let's say which have compact support in R3. Let's say, to be concrete, functions which are smooth and that have compact support by the formula we wrote during last lecture. The second use you can do of the Pauli-Jordan function is to build directly solutions of the Klein-Gordon equation, which are convolutions of the Klein-Gordon function over space-time. You see, in this other formula, you take, these are on R3, these are initial conditions. This is a test function which has compact support in the space-time, okay? This is obviously a solution of the Klein-Gordon equation. And we saw last time that all the solutions of the Klein-Gordon equation belonging to this class can be written like this. This is the first important statement. The second important thing we saw last time is that if we use now the Pauli-Jordan function to set up an inner product, a symplectic product, in the space of test functions, the Pauli-Jordan function is antisymmetric, as you remind. So this product, I'm taking here real functions. This product is evidently antisymmetric. So it's a symplectic product. Okay. But the interesting and important point is that we can rephrase this product by using the second fundamental property of the Pauli-Jordan function. The first one is that you can solve the Cauchy problem. The second is that you can write it as the difference of the retarded function and the advanced function. I use the word function, but I should say distributions. These are solution of the inhomogeneous Cauchy, the inhomogeneous Klein-Gordon equation with a delta source. If you use this property, you can show that this symplectic product can be rewritten as an integral at t equals constant of the solutions of the Klein-Gordon equation associated to the test functions f and g. Okay. So this is a space-time convolution. There are two space-time integrals here over the Pauli-Jordan function. This is an integral over a Cauchy surface at fixed constant, a time constant time. This psi g and psi f are the solution of the Klein-Gordon equation obtained by convoluting the Pauli-Jordan function with the space-time test function.
Sorry, this is inner product FG or inner product GF?
This is psi g, psi f. Psi f, psi g.
The sign is...
With this minus here.
The sign is opposite from what you said last class.
You can verify. I did the verification myself. If I said something different last time, maybe I was wrong. With this choice of sign, you get this writing of the inner product, where the derivative at first on the second function and after on the first should be correct, but verify it.
So understand the first inner product, that's on the space of test function.
This is
the second one's on the space of solution.
Yes, but this solution is obtained from the test function this way. And you see, this is an integral over three-dimensional surface.
Right.
This is an integral over R8. So this is the way in which the Klein-Gordon equation, Klein-Gordon inner product, which is the starting point of every textbook doing this kind of subject, is related to the Pauli-Jordan function in this case. And indeed, this way of writing encodes completely this. Here, you have this, all the properties of the Pauli-Jordan function present. The second thing is that, so we got this identity, Fg. I use the same symbol, equal psi f, psi g. But you understand that this is this convolution, and this is the standard Klein-Gordon inner product on the space of solutions, in this case, real solutions of the Klein-Gordon equation. But this second way of writing, so you know very well, I don't think I have much time to spend in explaining to you that this way of writing is indeed the integral of a conserved current. If you give yourself two solutions of the Klein-Gordon equation, you can construct a current, which is psi 1 d mu psi 2 minus d mu psi 1 psi 2. And obviously, this is a conserved current because Those are solutions of the Klein-Gordon equation. Every one of you knows the thing, I guess, but let's do it fastly. When we apply this operator here, we get twice d mu psi 1, d mu psi 2 with the minus sign in between. And then when d mu is, so these two terms go away. And then we get psi 1 D'Alembertian psi 2 minus D'Alembertian psi 1 psi 2. And here we use the Klein-Gordon equation. This is minus m squared psi 1 psi 2. This is plus m squared psi 1 psi 2. And this is 0. Okay? So, since this current is conserved, you can integrate this current over every Cauchy surface you like. You integrate G mu over d sigma mu, sigma, and this is because of the Stokes theorem. Does not depend on the surface, because here you have the integral on the boundary, and here you have the integral on the volume. So this form can be integrated over every Cauchy surface. So this is a conserved current we are integrating. This is the first statement. The second statement is that, by the way, this way of saying the things, if you define this Klein-Gordon product, you can now extend it to things, solution which are more singular than the one we were considering. So also solutions which do not arise this way, which are not the convolution of the Pauli-Jordan function with this function of compact support. Here we can extend this Klein-Gordon product to the space of solution. Even one solution can be a distribution. Take psi1 a distributional solution of the Klein-Gordon equation, and psi2 a sufficiently well-behaved. What matters is the behavior, the fall-off at space like infinity to have the conservation. You have to use the Stokes theorem first in a region which has this boundary, and then you have to remove this boundary at infinity and be sure that there are no contribution remaining here. Okay? So now, as I was telling the other day, this is the classical phase space, we can say, and we get commutation relation by promoting the Poisson brackets to commutators. This accomplishes the first step in quantization. This is the first step of quantization. In this way, we have constructed a non-abelian field algebra. We can do. We can also use the Weil operators if you wish. It is not necessary to enter in this kind of mathematical complication for our aims. But here is the construction that comes from the solutions, from the space of solution of the classical Klein-Gordon equation. And here we get the first step in quantization from an abelian algebra to a non-abelian field algebra, not that. The second step would be find a Hilbert space representation. Okay? This first step is unique. Is the second step, which is wildly non-unique. Okay. So just to complete this part, this can be the same things that you see on those blackboards apply literally word by word on curved spacetime. So here we move to curved spacetime. I don't know what is this thing. But we need a technical hypothesis. The hypothesis is global hyperbolicity. In a way, we are saying a tautology by saying this word, because a global hyperbolic manifold is a manifold in which the Cauchy problem can be solved in a global way. So we are telling that we are extending this method to those manifolds in which we can extend this method. So for global hyperbolic manifolds, should I remember the meaning of this word? I think not.
Do you mind just stating the definition?
The definition. So if you give us now, let's move to before coming back to Minkowski. Let's just rephrase this on the curved spacetime setup. So you have a pseudo-Riemannian manifold. Okay, so this is a Lorentzian metric on this manifold. And you ask for global hyperbolicity. Global hyperbolicity means that you can, the Cauchy problem. So if you have the pseudo-Riemannian manifold, the Klein-Gordon equation on it is obviously written by using covariant derivatives. And this is concretely on a global hyperbolic manifold. The Cauchy problem for this equation is globally well posed. Means that the manifold is, topologically speaking, R times sigma, where sigma is a space-like manifold. Or else that you can globally foliate your manifold with Cauchy surfaces. Okay? And given the initial data on one of these Cauchy surfaces, determine the solution everywhere. So Minkowski is an example of such a globally asymptotic manifold. But if you cut Minkowski, a strip of Minkowski, this is no more globally hyperbolic manifold. Okay? Because if you give yourself the Cauchy data here, you can uniquely determine your solution here. But once you are here, information can flow in from the boundary. An example of a manifold like this is anti-de Sitter, which is so widely studied these days. You can think of anti-de Sitter as an hyperboloid this way. It is non-globally hyperbolic in two senses. One, because there are closed time-like curves on this manifold. But this, you can solve this problem of periodicity by non-identifying the points when you come back. So going to the covering. But if you go into the covering, then you see that there is a boundary at space like infinity precisely this way. So if you give yourself the Cauchy data here on this surface, you can determine your solution in this region. And the information can flow in from this boundary. So anti-de Sitter is non-globally hyperbolic, but this is also the source of interest of this manifold, because this boundary at space like infinity is a copy of a Minkowski space-time in dimension D, if anti-de Sitter has dimension D plus 1, and the anti-de Sitter conformal field theory correspondence tells you that if you give yourself a quantum field theory inside here, you have, in a way or another, constructed something inside. Then you go to the boundary, take the restriction of the theory on the boundary. This will be a Minkowskian Poincaré invariant, conformal invariant quantum field theory. This is the content, roughly speaking, of the ADS CFT correspondence. So non-global hyperbolic manifolds have their own interest. The methods we are explaining in this course apply to global hyperbolic manifold. So global hyperbolicity means that you can foliate your manifold by hypersurfaces, which are Cauchy surfaces. And there is a theorem which transports to the curved space-time global hyperbolic case exactly what we said in the flat space. If you are on a globally hyperbolic manifold, you can uniquely identify the advanced and retard propagators, and you can form the analog of the Pauli-Jordan function as the difference of the retarded minus the advanced propagators. This, the existence of this is a consequence of the global hyperbolicity of the manifold. If you want to have a model, think of the Pauli-Jordan function. Of course, in the curve space, constructing it might be difficult. We will do it in the examples. But there is a theorem which is due to Leray and Lichnerovich, which tells you that this exists for a globally hyperbolic manifold. So you can do the same, the same path we have already worked on. Define a symplectic product in the space of test functions. By using the unique solution of the Klein-Gordon equation subject to the same initial condition I wrote there. Okay, this is unique. And then you can, by using the splitting of the commutator into retarded and advanced, you can transform this symplectic product into a symplectic product in the space of solutions of the Klein-Gordon equation, which you are going to write this way. Sigma is a Cauchy surface. H is the induced metric on the surface. T is the global field that you call time, so that hypersurface of constant time are this slice, and this variable x are variable describing coordinates describing points on this surface. N is the normalized normal to this surface, and you can show, because this thing is once more a conserved current, which you write in terms of the covariant derivative. This is a conserved current that you integrate on a surface, and you can transport it by using the Stokes theorem. So there's no difference between this and this, provided you add the hypothesis of global hyperbolicity. Global hyperbolicity tells you that there is this analog of the Pauli-Jordan function on a global hyperbolic manifold, and this gives rise to the Klein-Gordon inner product in the space of solution, and also on a globally hyperbolic manifold, quantization, the first step in quantizing a theory of a scalar field satisfying the Klein-Gordon equation, consists in writing the covariant commutation relation in this way. Here there is the I that renders the Poisson bracket, transforms the Poisson brackets into commutators. The scheme is precisely the same. There's nothing different, with the exception that you have to know a little bit of Riemannian geometry to deal with these expressions. Yes?
Sorry, I just noticed you erased it, but the way you wrote the way you wrote the Klein-Gordon equation in terms of the determinant of the metric didn't look right to me.
Which one?
You wrote 0 equals
1 over square root of G. You wanted this absolute value, maybe?
No. Well, it was more of what came after.
D mu, G mu nu, square root of G, D nu phi,
Okay.
plus M square phi.
That wasn't quite what you wrote last time, but.
Okay. What did I do?
You didn't write the del nu, and you didn't write the phi at the end.
I'm sorry, but it was intended to be there. Okay, so if you understand what to do in the Minkowski space, and if you have a understanding of what is going on in Minkowski space, quantum fields on globally hyperbolic manifold is nothing different. The only difficulty is that now, so the first step in quantizing a theory provides a unique answer. The commutation relations are uniquely determined. The second step, which would say you have fields in a algebra, phi. You want to represent them as operator in a Hilbert space in such a way that the commutation relation of these operators are the same. So you are representing your algebra. This second step, the answer to this second step is not unique. So the Stone von Neumann, this you can think of this thing as the canonical commutation relation, written in a covariant way. Before entering in this construction, let me show you that a theory that you construct this way in a curved space-time is local. Local means it satisfies local commutativity. If points are separated by a space-like distance, this commutator, even if you don't know it, is 0. Okay? How can show this? we can show this thing in this way. As I told you, you can, when we quantize a field theory, because of the necessity of putting the I here, we have to extend the Klein-Gordon product to complex solution of the Klein-Gordon equation. So the definition of the Klein-Gordon product to complex solution of the Klein-Gordon equation is now written this way. Let's write C1, C2. Okay, this writing represents the commutator C of x, y, because of the equivalence we have already seen. Okay, so let's check that this gives rise to a local theory. Means that if when you choose points that are space-like separated, this function vanishes. Okay, you can show. Suppose that let me use this. The covariant commutation relation. Now we are on a general manifold which is globally hyperbolic, okay? They express in a covariant way the equal time commutation relation. So give yourself a Cauchy surface, hypersurface sigma. This is equivalent, should be equivalent to this. Okay, but if you write the way you should write the equal time commutation relation this way, you can maybe wonder if the way you wrote things is or not covariant. Okay, means if it depends on the choice of sigma or not. So if you consider you can show, so consider the Klein-Gordon product of a function f with a quantum field phi. Okay, this means I f star of x and mu d mu phi This is a solution, and this is the field itself. Minus n mu d mu phi f star phi integral over the surface. This is the field, quantum field. This is a classical solution, okay? It's clear? This is a classical solution. This is the quantum field satisfying those equal time commutation relations. So you can prove, and this is a simple exercise that I leave to you as a home, that if you compute the commutators of the field you have smeared this way with the field you smear with another solution, this is minus f g star over sigma. But you know that this is independent on sigma. Okay, this is the Klein-Gordon product of these two solutions. It is computed on an per surface sigma, but we just saw that this is not dependent on sigma. So these commutation relations are also not dependent on sigma. So this way of writing the equal time commutation relation, which makes use of a chosen hypersurface, indeed do not depend on the chosen hypersurface. First thing. And second thing, since it do not depend on the chosen hypersurface, if you have 2 points, two points which are separated by a space-like path in between, and you consider the field here and the field here, because of this property, which do not depend on the sigma, these fields have to commute. This means that this function is 0 whenever 2 points are separated by a space-like path. It is clear? So make this exercise home. And these do not depend on sigma indeed. And so also this do not depend on sigma. Okay, this concludes the first step of quantization on globally hyperbolic manifold. You just have to find this function E. And the recipe you find in textbooks of quantum field theory and curved space-time is indeed the recipe to construct the function E. So let me tell you this because before going on, when you open, let's say, the Birrell and Davis book or any other standard theoretical physicist book, they ask to you to construct the Klein-Gordon inner product, which I've already constructed on a globally hyperbolic manifold. This is well posed. And then find the basis such that this is true, this is true, and this is also true. Means diagonalize your inner product. Okay? You are familiar with this. And then they say, write your quantum field this way as a sum. And you assume canonical commutation relation for these operators. Okay. This procedure is perfectly good and provides a unique answer for the function E. Means that if you now compute the commutators phi x, phi of y. This is c of x, y, the commutator function, which is minus IE x and y. And this is written as a sum over g, ug of x, ug of y star, minus ug of x star, ug of y. This expansion is unique. Is an expansion for the commutator. If you reshuffle the function ug by using, let's say, a Bogoliubov transformation, and next lecture I will completely describe what are Bogoliubov transformation and find the implementers and the DS matrix for any Bogoliubov transformation. This is the subject of the lecture of Wednesday. Even if you use a Bogoliubov transformation, this expression is always the same one. It never changes. So the expansion in mode of the commutator is uniquely as a unique answer. The non-uniqueness comes once you start asking that the vacuum of the Fock space is annihilated by the operators A. This choice provides a representation in a Hilbert space, which is non-unique at all. But the commutator is unique. So up to this step, the procedure provides a unique answer. Okay. So first, we can summarize what we have done up to now. And now, for the remaining part of the course, we will try to realize the commutation relation in Hilbert spaces. And this opens a certain amount of problems. And so we have a classical field. Let me put here a classical field, which has classical Poisson brackets. And you promote it to a quantum field which has commutation relations. Canonical commutation relation. Up to here, for globally hyperbolic manifold, this problem has a unique solution. Now we want to find representation of such canonical commutation relation. I won't overwrite this at over the represented field, but this problem is now the problem we have to face. How could we represent this field algebra in a Hilbert space? As we were discussing before, there is an answer in the book by Wald, but we can try to simplify that answer. And before entering in the details of some constructions, let me tell you what are the properties. What are you looking for? And what are the properties of such object you want to construct? So here we are constructing the commutator. The rest of the construction amounts to construct the two-point function. We can think of what properties this two-point function we want to construct has to have before, for instance, describing what happens once more going back to Minkowski space. So suppose suppose you are now constructing a representation. Phi of x goes into an operator. And you suppose that in your representation, there is a cyclic vector that you call 0. What does it mean? It means that if you apply polynomials in the field to this vector, which is cyclic, and you close this set, you get the whole Hilbert space of the theory. Okay? Since we are constructing quasi-free theories, linear theories, all the content of the theory is encoded in the two-point vacuum. Let's call this vector the vacuum, even if it is not vacuum. Vacuum to vacuum correlation function between two fields operator. This is the linearity of the field that tells you that this object is going to encode the whole set of properties of the theory. Okay? Because if you are studying a linear theory, endpoint functions can be written as product of two-point functions. The truncated endpoint functions vanish. Okay? This is not true if you want interacting field theories. In this case, the two-point function does not encode the whole content of the theory. And by the way, as you know, probably up to this day, today, no one can solve a relativistic quantum field theory in dimension 4. The problem of reconciling relativity and quantum mechanics is still open. We do have perturbation theory, but we don't have a construction for such object. And the difficult property to be shown is the positivity of the theory. I will come back on this point maybe. So we want to construct the two-point function, which in a way encodes, I will show you how, encodes all the properties of the theory, and you immediately understand what is the relation of the two-point function with the commutator. Since this is a multiple of the identity, we can take the vacuum expectation value of this difference, which tells you that the commutator is the difference, has to be the difference of the two-point function and the permuted two-point function. So if you know a two-point function, the first thing you have to check if it satisfies this functional relation. So this is the fundamental property a two-point function has to satisfy. This is the two-point function. This is the so-called permuted two-point function. Sometimes you can find in textbook another symbol for the permuted two-point function. W prime x, y is precisely w of y and x. Okay? When you have two symbols, there are two permutations of those symbols, of course. If you have n symbols, there are n factorial permutations of those symbols, and they play a role in constructing quantum field theories. You have to consider not only the Weidmann functions, but also all the permuted ones. For instance, to go to the Euclidean section. This is I will tell you some words about this. So you see the commutator. If you now revert the writing here, if you give yourself a 2-point function, you can write it as a symmetric part and an anti-symmetric part. Okay. Or let's say anti-symmetric part. As any function. You can write w of x and y as w of x and y plus w of y and x over 2 plus w of x and y minus w of y and x over 2. This is the commutator over 2. And this is, maybe you may call it the anti-commutator. Sometimes you find it the symbol G1 in box. You see, this is a symmetric function. This is an anti-symmetric function. This is completely determined by the canonical commutation relations. This is totally arbitrary. So the quantization gives you a unique commutator which solves the Klein-Gordon equation. You need to specify now. So this is the content of the equation of motion. If you give yourself a Lagrangian, the Lagrangian tells you the commutator. It don't tell anything about a symmetric solution that you can add. Note that a symmetric solution do not contribute to the commutator, of course, because s of x and y minus s on y and x is 0. So this is, in a way, a classical function you can add here. You have the commutator, and you have to add the classical function. Let me speak in this way, which is not very precise, but this function do not contribute to the commutator to get the 2-point function. And the 2-point function is the Hilbert space of the theory, as I will show in a second. So you don't have the equation of motion. Of course, this symmetric function has to solve the equation of motion also. In this sense, it is determined by the equation of motion, but it's largely arbitrary. Okay. Not completely arbitrary, because if you want to construct a Hilbert space out of the 2-point function, you have to impose the positivity condition. What is the positivity condition? It means that W of f and g, which is W of x, y, the same convolution we were considering for the commutator over space-time. This must be a positive product. Means that W on f and f bar, let's say, and f, which will be interpreted as the norm of the quantum field applied to the vacuum. This is one particle state, has to be positive. So this has to be a positive definite distribution. This is the only necessary requirement you have to impose to the 2-point function. If you have such positivity, then you can construct your Fock space operators and everything. Okay, I'll do it in the Minkowski case just now. Yes.
What do we mean by WXY bar?
No. There is no barrier. This is a remaining of an old thing. Okay, so let me summarize, add something to our summary. We have arrived here. This is uniquely fixed by your Lagrangian. But to quantize the theory, you need to add something. This symmetric solution, which is not fixed by this. So that renders quantum field theory non-unique, and quantization of the same canonical commutation relation comes in plethoras. Okay. So you were asking me about this book. Huh? The mu, you have seen in this book a real functional on the space of real solution of the Klein-Gordon equation. It is just this function S. You can tell this way. So the arbitrariness you find in quantizing a theory is the arbitrariness in choosing this symmetric solution of the Klein-Gordon equation that you can add to the commutator to build the two-point function with the only necessary requirements that it has to be a positive distribution, positive definite distribution, in order to get the quantum mechanical interpretation of the theory. By the way, you know the positivity of the Hilbert space of the theory is incompatible with gauge invariance. And this also complicates things when we want to solve really solve a physically interesting model of quantum field theory, for instance, quantum electrodynamics. If you ask for locality, Lorentz invariance, locality means local commutativity, and Lorentz invariance, then you can't. Positivity is incompatible with the gauge invariance. If you have standard quantum field theories, which by the way are not interesting for physics, because all models describing the real world are gauge quantum field theories, the positivity is not compatible. You just have to work with the space in which positivity does not hold, and in the end apply a supplementary condition like the Gupta-Bloiler or BRST condition to select the physical space. So we are insisting on this property here, but if we were interested in gauge quantum field theories, we should abandon also this property. Okay, we may want to make a break of 5 minutes. Yes.
So if I'm reading this right, the positivity condition means that SXX has to be positive?
No.
Well, in as much as
it's W, which is positive. But
yeah, what does that say about S? That's what I'm asking.
S is compensating for the non-positivity of C. Mm-hmm. I will show you in an example. It may be clearer in a few minutes.
Sorry for this morning. I know you waited for me.
Mais je parle lundi matin, c'est peut-être pas un bon jour. Hein. So let us try to now explore what are the possibilities going back to the Minkowski space, and we try to find a Hilbert space representation for the commutation rules built in terms of the Pauli-Jordan function. Okay, this is flat spacetime. This quantization rule is unique for the Klein-Gordon field. But finding a Hilbert space representation has no unique answer, and the answer can be rendered unique by making a certain number of hypotheses. Okay. Last time I described what are the hypotheses you do in standard quantum field theory. Okay. Mainly, you ask for, so the algebra is invariant under the action of the Poincare group, but this does not mean that the representation is invariant under the action of Poincare group. If you have a symmetry, you see the commutator is Lorentz invariant, but the two-point function need not to be Lorentz invariant. For instance, okay, when you have a symmetry of the algebra which is not a symmetry of the representation, you speak of spontaneously symmetry breaking. Spontaneous symmetry breaking means that you have a symmetry at the algebraic level, which is not a symmetry of the representation. In the standard case, you ask for relativistic invariance of the representation. And positivity of the spectrum of the energy momentum operator. These two requirements uniquely select a quantization, as you all know very well. But you cannot dispense with either one of these assumptions. Otherwise, you open a lot of other possibility. I think you are familiar, but standard quantum field theory courses, I'm talking with the students, of course, of how you construct the representation using these requirements. You start by constructing a basis. Let me not put the hat over the operators. I'm now talking about the representation. You construct the Hilbert space in standard approaches by diagonalizing the energy momentum operator. Are you fresh with this construction, or should I do a brief summary of it? We do it? Or you have done recently? As you prepare to do it?
It would be interesting to see how it works in infinite dimensions. Like,
we are in infinite dimension here.
Yeah. I mean the diagonalization.
This is the diagonalization. This is the starting point. So the operators of translation are acting on the basis this way. We are talking about the one particle Hilbert space of the theory. This is the base for H1, the one particle space. Okay. From here, you also understand that U of lambda k is lambda k. So this is the vector parameterized by the four momentum k. K0, K1, K2, K3. And this is the vector parameterized by the form momentum lambda k. You go from here to here by commuting u of a with u of lambda, and by knowing that this is u of lambda minus 1a. So you apply this to k, and you get e to the I k lambda minus 1a u of lambda of k, and this is u of lambda k, a to the I lambda k a. Here always there is the Lorentzian inner product here. Apply to u of lambda k, and this shows that this is proportional to lambda k. This is the first step. So how the representation of the translation group act, how the representation of the Lorentz group act on a basis of states which diagonalize the energy momentum. Then you construct since k is a basis, you can expand the identity operator in such a basis. Then you apply u of lambda u to lambda minus 1 here, and this is equal to 1, which is equal to this thing, which is equal to d mu of lambda k k, because you have here lambda k here, and then you make a change of variables, and you get the mu of lambda minus 1k here. So the measure, you see, has to be Lorentz invariant. And here the Lorentz invariant measures are classified. And since we have imposing positivity of the spectrum of the energy, in every Lorentz frame, this measure is completely fixed by the fact that the mass is an invariant of p squared. If you give a value to this invariant, this measure is fixed. Is theta k0 delta k squared minus m squared. The normalization you put here is 1 over 2 pi to the cube. So what we have asked for, representation of the Poincare group on the basis and positivity of the energy that you can write also. Here you can integrate d for k, yeah? But you can integrate what the dk0 variable and write this equivalently d3k over 2 pi cube 2k0, because this delta is delta of k0 minus k squared plus m squared over 2k0, because the other thing is killed by this theta. So k, where it is intended that k is square root of k0 plus of k squared plus m squared k. Okay, and then you here this resolution of the identity gives the normalization of the states. If you put here a k prime, this equal k prime. This has to be equal to k prime. So the scalar product of k prime is 2 pi to the cube 2k0 delta of k minus k prime. This is the relativistic normalization of the states.
Sorry, that's the identity operator?
This is the identity operator because this is a basis. So we have to find what the measure is. And we find it because of the Lorentz invariance. And here, this theta k0 enters because of the positivity of the energy. This is the crucial step. Huh? Don't overlook this point. This is the crucial step of quantum field theory in standard textbook. We will comment on this. So what you do next? So here you have completed the construction of the one particle Hilbert space. We have a basis, we have the normalization, and we have the representation of the Lorentz group. Of course, these states are improper states. These are improper generalized eigenstates of the momentum operator because they are not normalizable. So what is normalizable is a state in which you superpose such states. So a state F, what is it a state F? Is just an average over the states with a test function in momentum space depending on the three momenta in such a way that the scalar product here you see it of f and g is f star k g k d3k over 2 pi cube 2k0. I've used here the normalization of the states. So this is the scalar product in the one particle Hilbert space. Okay, this is the standard way you do this construction. I could do it in one step by just using the 2-point functions. We will do this after. Okay. Then what you do is to construct the Fock space of the theory. May I go on the question here? The Fock space of the theory, you construct the vacuum. The vacuum is the unique invariant state under the representation of the translations. And then you construct a symmetric Fock space over H1. Okay? So you construct states that you label with n momenta, which are completely symmetric in such momenta. Okay? And such that the scalar product Q1, Qn, K1, Kn is 1 over n factorial, the sum over all the permutation belonging to the symmetric group of n elements, Qe, Q1, let's say, K P1, Qn, K Pn.
So are we summing over?
The symmetric group
It's the space of
permutation. So this you have a permutation 1n, pi 1, pi n is another ordering of this. And you sum overall the possible permutation, and you divide by n factorial. This is conventional. You could also not divide by n factorial, and then formula change a little bit. Okay? So this is the, once you have constructed the one particle Hilbert space, this is the basis of the symmetric Fock space over H1. And in the last step, you construct the ladder operators. You define the creation of a particle of momentum k acting on k1, kn is square root of n plus 1. This is because we are choosing this normalization here this way. K, k1, kn. And then you can compute, this you define this way, and you compute the corresponding annihilation operator. This is a calculation. You suppress the kj here, and you take the inner product of k with kj, and you sum over all the possibility by dividing by 1 over square root of n, and this is the adjoint of this. Okay? So we are constructed this way, the symmetric Fock space over H1, in the ladder operators, and in the last step, you want to construct the field. You can do the construction. I mean, you can not write the answer at the beginning, but write just a function which depends on k and x times a of k plus a function plus its conjugate times the adjoint, and you integrate over the measure. This is not the standard normalization. Then we will come to the standard normalization after. Okay. And if you impose, this is the represented field, that it has to satisfy the, it has to be covariant. Now you impose this. This step is taken in the notes that I will send you. Yes?
Sorry, am I reading this right? Is there a left bracket before AK and a right bracket after a dagger K?
This is.
Oh, okay, so.
This way. If you impose this, then you get that this has to be e to the minus a kx, which means minus a k0, let's say square root of k squared plus m squared. This is k0. T plus ekx. And this is aekx, the complex conjugate of this. This is because you want that Lorentz symmetry is a symmetry of the representation. But you are not obliged to do this. You see what I mean? The choice of this function here is selected by Poincare invariance. The details of this step, I'm sorry, this is here, of course. Okay. This is e to the ikx. In the general case, you have two functions here. But if you impose Poincare invariance, you get these exponentials. Because you know very well that the exponentials are characters of the translation group. And that's the crucial property that selects this answer. Okay? So in this way, we have constructed a Hilbert space and a field, and you can check that the commutation relation for this field are precisely the right ones. Okay? If you, in the end, change the normalization of this field to get here the square root, because these operators, I didn't say, but the operators AK, A, K prime, satisfy the commutation relation K, K prime, delta, K, K prime. So there is here a 2 pi cube 2k0 delta of k minus k prime. So they have the relativistic invariant normalization. If you want creation and annihilation operators that satisfy standard commutation relation, just a delta here, you have to divide here by this a square root of this. So you put a square root here and a square root here. So you get the same expression. And you call all this object A, and all this object A. Okay? This is the standard construction. You ask for Lorentz invariance and positivity of the energy. You build a basis diagonalizing the for momentum operator, and you turn the machine by imposing Lorentz invariance and translation invariance at each step. So we have constructed this way a quantum field theory whose vacuum expectation value we can compute. If you do the computation, so the you see, this is, so let me rewrite the field. No, the field is written there. Do the computation is extremely simple and immediate. This means that in the Pauli-Jordan function we had two components. As you remember, the Pauli-Jordan function is not the Pauli-Jordan function. The commutator is 1 over 2p cube epsilon k square delta of k square minus m square, which has two components. One which has positive energy, one which has negative energy. And we just selected the component which has positive energy. So we have splitted the commutator in momentum space. Yes?
Sorry, should there be a minus I in front of the D? I can't tell whether or not that was that.
Minus ID is the commutator. So you see, this is the support of the commutator in P space. And the two-point function is the commutator multiplied by theta P0. So this is W of X and Y. And this is minus W of Y and X, the permuted function. Okay? So this is the standard way of doing this construction. Let me add just one other way to do it directly. There's no more white chalk. So to come back to our first way of looking at the thing, we have to find a distribution solving this equation. We can write this equation in Fourier space. Since this is invariant under the translation group, it depends on the difference variable. Also, this depends on the difference variable. And also, this depends on the difference variable, but minus the difference variable. Okay? This is the two-point function. This is the permuted two-point function. Let's Fourier transform with respect to this variable x minus y. So I call psi the variable x minus y. So here I get C of psi, the commutator, is W of psi minus W of minus psi. Okay? Then I apply the Fourier transformation with respect to this variable psi, and I get the equation C of p equals W of p minus W of minus p. Okay? In this particular case, C of p has already this structure. Okay? The structure is already this way. C of p has two components. One is W of p. You can call this one W of p, and this one minus W of minus p. Okay? So this is the positive energy part, and this is the negative energy part. Okay? So if you just select the positive energy part here, W, the Fourier transform of this term is the two-point function, and this is the standard solution you could have get directly by solving the Klein-Gordon equation by Fourier transformation. You have to solve this equation. So you write the Klein-Gordon equation once more in the difference variable, W of psi. This is by Fourier transformation minus p squared plus m squared W of p, which has a solution has two components, alpha theta p0 delta of p squared minus p squared plus beta theta minus p0 delta p squared minus p squared. And observe that alpha and beta are generic functions depending on p. But if you want Lorentz invariance, they cannot be. They cannot depend on p. They can depend only on p squared. But since p squared is delta m squared, they are just constant. And then you kick out this term, because this does not satisfy positivity of the energy. And you end up with one solution, which is fixed by Lorentz invariance. So the function here is just a constant. And you reject this term because it does not satisfy positivity of the energy. Okay? So you Fourier anti-transform, and you get the two-point function, which is precisely the one we have found at the end of this construction. Okay. So this two-point function, as I said, you encodes all the features of the theory. Let's see how it encodes the Fourier space, the one particle space. It is encoded because when you define the inner product on test functions, these are functions belonging to, let's say, C0 infinity over 4 with complex values, or you can put here the space S of fast decreasing function. Then you compute this scalar product. You compute it by Fourier transformation. if you Fourier transform this convolution, you get 1 over 2 pi cube d3k over 2k squared plus m squared. This just by Fourier transformation with this formula f tilde of minus k, this minus because the Fourier test function is transformed by the opposite sign with respect of distribution, k, g. This, don't concentrate your attention on this minus sign. They don't mean anything because this is just a function of a tri-momentum, and this is another function of tri-momentum. Is precisely the Hilbert space we got at the end of our construction. So you see, the Hilbert space is already there, and the Fock space is obtained when you define the fields operator phi of x in terms of W in x space, not in momentum space. There's another way of writing the field operator, which we wrote somewhere here, directly in x space. I will do this later or the next times, because I wanted here to end this lecture by finding another interesting solution of the splitting equation. Okay, let's do this. So let me, we said, we are considering now solutions of the Klein-Gordon equation, which are translation invariant, but not necessarily Lorentz invariant. Okay? So our fundamental equation, which encodes everything, is this. Since there is translation invariance, the commutator always is Lorentz invariant also. But the two-point function has to depend on the difference variable. If we Fourier transform with respect to the difference variable, we get the same functional equation. You see, it's in a non-differential equation, this. It's a relation between these functions. You have to find a W which reproduces the commutation this way, and as I told you, this amounts to find the symmetric part, which is not fixed by the commutator, okay? In Fourier space, this equation is written this way. Okay. We are doing something which is very important. I'm constructing the KMS representation now. I try to do it in the simplest possible way. So, the solution in the previous case, you see, was the simplest one. W of P was just theta of pi 0, the Heaviside function, times the commutator. Okay. While W's of minus P was theta of pi 0 of minus pi 0 times the commutator, but the commutator is antisymmetric, so this was theta of minus pi 0 times the commutator, theta of minus pi 0. Okay, in this way, You see, this was the previous case. So let's generalize this and write here this ansatz, a generic function of P. To be simple, we put a function of P0. But we could put a generic function of P here, make this ansatz. Okay. So what is W of minus P? W of minus P is F of minus P0, let's say P0, times C of minus P. And C of minus P is minus C of P. So this is minus F of minus P0 times C of P. Okay, so you see, if we put this inside here, we get F of P0 minus F of minus P0, but more generally, you can have P times C. So C is equal to this. This means that F has to satisfy this simple relation, F of P0 minus F of minus P0 equal 1. Am I wrong? Plus F of minus P0 equal 1. Plus. Because here I changed this sign, yeah? Plus. Okay. This is obvious in the case of theta. Theta P0 plus theta of minus P0 equals 1. This is the function which is 1 here, and this is the function which is 1 here. Okay. So this is generalization of this. Any function which satisfies this provides a good quantization of the theory. Surely will not be Lorentz invariant. Okay, but the commutator is Lorentz invariant. So let's try something. There is one function which solves this thing. So you see, our model is this. We try something which is like this. Now, you see, this is the step function. Let's try something which is a smoothed out step function. So let's do this ansatz. F of P0 is 1 over 1 minus the exponential of minus beta P0, where beta is a number, positive. Okay. Let's verify that this solves this equation. Minus 1 minus 1 minus a to the plus beta P0. This is, of course, this has the nice property that the sum of these two things is plus. The sum of these two things and the product of these two things is the same thing, because the sum is 2 minus eta minus beta P0 minus eta to plus beta P0, and the product of these two things is 1 plus 1, because this is the same exponential with different sign, opposite sign, times 2 minus a to beta P0 minus e to the beta P0, and this is 1. Okay. So, as a consequence, you can define a two-point function W beta of x and y, which is the commutator, 1 over 2p squared, 2p cubed, e to the minus e p x minus y, epsilon of p0 delta p squared minus m squared divided by 1 minus e to the minus beta p0. This is the two-point function. Okay? And because of that property, this two-point function is local. It satisfies the canonical commutation relation. The same commutator. This is a solution of the Klein-Gordon equation. This is obvious. The commutator does not depend on beta, while the two-point function depends on beta. And you have to check positivity of this thing. So you have to check that if you compute this thing, this is greater or equal than 0. This is a little exercise that I leave you home. This representation of the canonical commutation relation is known under the name of the KMS representation at temperature 1 over beta. It describes an equilibrium quantum field which is in an equilibrium state, which has an equilibrium temperature, which is the inverse of this number beta here. Okay? We can rapidly show what is the feature that allows to you to interpret this quantum field theory as an equilibrium thermodynamical state. And so there is an easy way to characterize the mathematical properties of this quantization in terms of the analyticity property of this function with respect to the time variable. Okay? Which are equivalent. So let me tell you the abstract, and then I will do maybe the derivation next time. So you see here you have this epsilon. Epsilon is the function which is +1 when p0 is positive and -1 when p0 is negative. Okay? So you can write this denominator by splitting using the sign of p0. So this expression is equivalent to is equal to this. So we have two components on this W. One is the component where you have the theta, 1 minus A minus B P0. P0 here is positive. So this number is smaller than 1 here because it's minus beta P0. And then this part is manifestly positive. And the second part, you will have minus theta minus P0 here, but you change this in a plus, and you change the sign of the denominator. Then you get e to the minus beta P0 minus 1 here. Then multiply the numerator and the denominator by e to the beta P0, e to the beta P0. And this is going to be 1 minus a to the beta p0, and notice that now p0 is negative. So this number is again smaller than 1. And you got a plus sign here. And this already shows for you the positivity of the thing. Of course, there is e to the minus epx minus y. And then you develop this as a series. You are going to write e to the a minus beta p0 equals the sum of e to the b beta p0 n. N goes from 0 to infinity. And the same for the second thing. So you make these developments in series. Let's do it for this term, for instance. This is a rather formal step, but I can give to it rigorous meaning. So this is going to have the aspect of a sum. Sum n going from 0 to infinity, 1 over 2 pi cube, e to the minus e p x minus y minus e beta p0 n. You see? Times theta p0 delta p square minus m square. So this is the zero temperature two-point function we constructed before. So this sum is something like plus the second part. Huh? So this sum is something like sum of W0, the standard positive energy two-point function at t minus e beta n x, s, and y. Okay, because there is this shift in the exponent. So you are taking the two-point function at n equals 0 plus copies of the two-point function at imaginary times, and you add as a sum. And then you get also the second term. The second term is, so this is the sum from 0 to infinity, plus the sum from 1 to infinity of the permuted one, sy t plus cn beta x. This is the thermal two-point function as the form of this infinite sum. So this shows that this particular quantization can be completely characterized in terms of the following two mathematical conditions. The two-point function W of t, x, s, and y is analytic with respect to the complex t variable in a strip, such that the imaginary part of time is in between minus beta and 0. Okay? The permuted two-point function prime is analytic in the opposite strip here. And there is a periodicity condition, which is called the KMS condition, that tells you that W of t, W of s, let me write it precisely. I will redo this next time, maybe, because from here we can, in one line, show what is the Unruh effect, and in 3 lines, the black hole temperature. Because what is going on, so once we have characterized the analyticity properties of thermal states, for instance, the Unruh effect is nothing else. Looking at the analyticity property, we can show what is the Unruh effect in 5 different senses. One, and the simplest one, is this one. We are translating the analyticity property of the two-point function in the vacuum by looking at it in the coordinate of the Nauru observer, Rindler observer. When you do it, the cut plane, I will tell you this in details next time. The cut plane of the two-point function when you have positive energy is mapped into a strip. And you get these boundaries are the opposite boundaries of this cut. So the vacuum properties, the energy properties, the positivity of the energy implies certain analyticity properties. And when you look at the same properties from the viewpoint of a Rindler observer, they appear as KMS properties. And there is a reason which I will explain next time why you can interpret this as a statistical state at fixed temperature. So let me finish by writing what is this periodicity condition. Then we will redo it because of its importance. The periodicity condition says that W of S, Y, I'm writing, distinguishing the time and the space coordinate, T and X. So I'm looking at the permuted function is equal to W of T minus E beta, X, S, and Y. This property, this periodicity property, plus analyticity in a strip are the characteristic property that you get when you would like to compute, but this object does not exist in the thermodynamic limit, the trace, the statistical average at inverse temperature beta of two quantum fields. If you could compute this thing, and you can if you put your system in a box, this thing is completely characterized by this mathematical property. This mathematical property survives in the limit, in the thermodynamical limit, while this does not. This mathematical property is characteristic of the KMS representation, and you have seen here how simply it is obtained in this scheme. You simply split, you have split the commutator in P space by this function in the vacuum sector. So you have used a step function this way to split the commutator in two parts and solve our functional relation. The thermal states are a splitting in which you use a theta function in which the splitting is smooth, and you allow negative energies in the reservoir. I will start again from this on Wednesday. We finish this, and we do a complete treatment of the S matrix for the Bogoliubov transformations.